Okay, so today, apologize first of all for not being able to be on last night, but I'm going to go ahead and make up for that right now and go ahead and walk you through our next portion, which I promised to you before spring break. Hope everybody had a great spring break and that you were safe. I know several of you guys are working and staying busy with that. Um, And so hopefully you're staying safe and healthy and your families are safe and healthy. And we will meet again tomorrow night at 6:15. We'll try to get back on our Tuesday and Thursday rotation of 6:15 each night. I'll send that out via Remind. Also, just make sure that you're catching up on old work that needs to be done. Really, if we look at the grand scheme of things here, we're about 4 to 5 weeks and then we're done, right? We're done with this course. And some of you will be moving on to becoming seniors. Some of you might be graduating, all of that good stuff. But it looks like maybe at this moment that we may not go back in May. I don't know that yet, but we'll wait and see what the governor has to say. I believe he's going to make a decision on that next week. So we will find more out. Hopefully, maybe we can see each other in May. But if not, we still only have 4 or 5 weeks left, and you do have a final you're going to take. I've got some other projects between now and then that you need to do that are counted as test grades, right? And some homeworks and stuff. So anyway, let's jump in today. If you have questions, email me, and I'll try to reply to you as quickly as possible. I do check that several times throughout the day. So we're going to start today by looking at geometrical isomers. So you should be able to see my screen, right? Geometrical isomers are isomers which have the same molecular formula and the same molecular structure. And I'm going to stop right there for a minute because, again, you need to take notes during this, right? I know it's like, whoop, it's right there on the screen. Yes, it is. But then once the screen disappears, you're not going to know it, right? If I was to move the screen out, even though you have read it, you have seen it with your eyes on the screen, but if I flip to the next slide and say, okay, what's a geometrical isomer? Most of you are going to say, I had no idea, right? So it's always good during these times to set and bullet some points down, make some notes. Again, statistics prove, it gets in your head at a deeper level by actually taking the notes while you're doing this, not just reading it, okay? So geometrical isomers are isomers that have the same molecular formula and the same molecular structure. In other words, they have the same atoms and the same bonds. Okay, and I'll show you what I mean in just a minute. However, the isomers are different because some of the atoms are arranged differently in space. 3D, three-dimensional. That's what we're talking about. So we talk about space. And the isomers cannot, underline, cannot be interconverted without breaking and remaking covalent bonds. Okay. Well, lots of good stuff there in that first slide. Definitely take some time, jot those things down. This is recorded. You have the ability to push pause, right? To freeze the screen, whatever you need to do to get it down. Take advantage of those things. It's not all confined to alkanes, right? Not to all confined to alkenes. What we're going to look at today is something called cis-trans isomerism, right? Cis-trans isomerism. I told you, I think we mentioned this last week before break. It's kind of like right-handed, left-handed type situations. But they are confined to compounds containing the carbon-to-carbon double bond, right? Remember, you're going to have a carbon dash dash carbon double bond, which is typically the alkenes and their derivatives. But cis-trans isomers, however, also occur in transition metal complexes and compounds containing only one single carbon-to-carbon bond. So they can happen with doubles or they can happen with singles, right? And not just in alkenes, but now it could also take place in transition metal complexes. Okay, remember your transition metal, that wide swath of metals on your periodic table, right? So how does this arise? Well, alkenes have two substituents, two different substituents at each end of the double bond. So it can exist as two configurational isomers. Simple alkenes can be defined as cis or trans, depending on whether substituents at the different ends of the alkene are on the same side. If they are on the same side, those are called cis, or if they're on opposite sides, we call those trans, right? So cis would be that two of those substituents are on the same side, or if it's trans, they would be split, right? One side on the other side. So that's the difference between cis and trans. You need to know that. So let's look closer. What does it mean to be on the same side, right? Obviously, we're talking about three-dimension here, so it gets a little bit more in detail than just same side, okay? So groups on the same side of the double bond for cis-trans purposes are on the same side of an imaginary line that runs through the nuclei of the double bonded carbon atoms. So you've got a great example here on your screen, right? You've got the line going through the double bonded carbons right there, okay? If you notice on one side, the underside, the bottom side there, you've got the hydrogen atoms are on the same side. On the other side, you've got methyl substituents are on the same side. So CH3, H3C, they're the same thing, right? What do you mean, you ask? Well, this is what I mean. How many carbons do you have in CH3? Got one carbon, right? How many carbons do you have in H3C? You got one carbon. How many hydrogens in CH3? Well, self, you got 3. How many hydrogens in H3C? Well, I still have 3. So what we're saying is basically that H3C and CH3 are the same thing. They're just written a little differently, right? And how they look. Kind of like I talked about last time, that right to left-handed type situation, right? If you don't believe me, you could look at the word ambulance, in your rearview mirror, and the way that it's written, it says ambulance, right? If you've never noticed that, if you have an ambulance coming up behind you, look in your rearview mirror. It's written backwards so that in your rearview mirror, you see the word ambulance. But now if you get out of your car and you look at the front of the ambulance, it's spelled backwards, right? It's the same thing. It's still ambulance, but it's the same thing we're dealing with here. If you're looking at it head on, right, it might be H3C. But if you turn around and put it in your rear view mirror, right, you're going to see CH3. But it's the same stuff. That's what I'm trying to get you to see, right? And so cis-trans, we have this division line between the two carbons, right? And you have methyl substituents up top. In this case, you've got hydrogen atoms on the bottom, right? But they're on the same side, right? So hopefully that kind of clicks with you. All right. Other names that you might see for cis-trans isomers, right? Geometrical isomers, you might see it called that. You might see it called configurational isomers. And the one that was popular is called stereoisomers, right? And stereo just means that you see them in 3D on both sides, right? That's not just mono, it's in stereo, right? So it's a good way to think about it. Substituents, we talked about substituents before. These are groups of atoms that have been replaced or substituted, right? Atoms of an original compound. Hence, the ethyl group in the compound on the following slides, we're going to look at a slide here coming up. The ethyl group on the following slide can be viewed as a substituent on ethene because it substituted itself for one hydrogen atom of the original compound. Okay, so let's look and see what we got going on. So there it is, the ethyl substituent, right, on the ethylene molecule, right, is there. In spotting cis-trans isomers, it helps to draw compounds as if they were substituted ethylene molecules as above. And we're drawing this out, and so we're putting in our CH2, CH3. That's ethylene, right? And so it just helps to draw that out the way that they have. So just kind of help you get a balance of really what is going on. Okay? All right, let's move on. So after deciding if they are cis or trans, the molecules must be named according to the longest continuous chain. There again, nothing different, right? In every single one of these, you've been naming them according to their longest continuous chain of carbon atoms. No surprise, right? So hence the compound seen on the previous slide is but1-ene, right? Notice its name is not a derivative of ethene, since the longest carbon chain contains more than 2 carbon atoms, right? More than 2 carbon atoms, right? If we go back, there's more than 2 carbons, right? Really, you get 1, 2, 3, but on the second one, then you've got the ethyl, right? Popping off, that ethyl substituent, the ethene, right? And so that's how we come up with that. So we get but1-ene. A little different, but we still go with that longest carbon chain. Requirements for cis-trans isomerism. There should be a double bond in the molecule. You're going to look for that, right? You're going to be looking to see, is there a double bond, right? If there is, then, you know, we can look at cis-trans isomerism. The 2 atoms or groups attached to each double bonded carbon atom should be different. Say that again. The 2 atoms or groups, substituents, attached to each double bonded carbon should be different. If they're not, right, then that's a different situation. When one of the double bonded atoms carries 2 identical groups, then the alkene is tri, right? Alkene is tri or tetra, in this case, substituted. So it could be tri-substituted, it could be tetra-substituted. But in either case of the tri or tetra-substituted alkenes, the easy system of nomenclature replaces cis and trans, right? All right. So since easy nomenclature is not required knowledge, spotting cis and trans isomers are fairly easy. Fairly easy. This is because there will always be 2 hydrogen atoms among the 4 groups attached to a double bonded carbon if a compound can possibly exhibit this type of isomerism. Now, let me stop and pause right here for a second, because I know some of this you're probably thinking, zoom, zoom, it's going over my head, right? But really, all I'm really wanting you to take out of these 22 slides is the fact of what is cis, what is trans, what is geometrical isomerism or stereoisomerism, the definition, right? And how do you spot it? That's all I want you to take away. I'm not going to ask you any deep, dark, probing question over this, but I need you to know the definition and how to recognize it, right? And then how to name it. That's it. That's all I'm going to ask you to do, okay? So how to spot the isomers. If one of the double bonded carbon atoms has 2 hydrogen atoms, cis-trans does not occur. Say it again. If one of the double bonded carbon atoms have 2 hydrogen atoms, it can't be cis-trans. Boom. But if both hydrogen atoms are on different carbons, cis-trans can occur. The cis isomer is the one with the 2 hydrogen atoms on the same side, right? And then the trans would have them on opposite sides, okay? So let's consider C4H8, okay? This compound has 4 isomers, which means it could show up in 3D in 4 different configurations, right? So let's look at each one. So one possible way is the but1-ene, right? You've got your double carbons. If you draw your line down the middle, right, the compound has no cis-trans isomers because you got 2 hydrogens down on the bottom, right? Due to 2 identical hydrogen atoms on one of the doubly bonded carbon atoms. Boom, right? That's it. So it's not a cis-trans. It's just but1-ene. That's how you would name it. Notice that when we're trying to figure out if there's a cis-trans, the double bond is written at the center of the molecule, and 4 groups come out of the 2 carbon atoms diagonally, right? Which is what we just saw. Back that up. 4 of these puppies come out diagonally. So there's a diagonal, there's 1. Diagonal 2, diagonal 3, diagonal 4, right? That's what we're talking about. The compound is not written as a straight chain or straight with perpendicular branches because this makes cis-trans isomers harder to notice. So we don't get this whole, linear thing that we've been dealing with, or straight branches anymore. Okay, so it's a little different. Isomer number 2, you get what's called 2-methylpropene. 2-methylpropene, right? Again, there's no cis-trans is possible because there are 2 identical groups on both of the doubly, right? So in this case, you got an H and an H, and you got a CH3 and a CH3, right? And so because of that, you can't have cis-trans, right? You're not going to get that. Isomer 3, you get something called cis-but2-ene. Now, this way it's going to work. But the reason it's working is because it's called cis-2-butene. It is the cis isomer. Why is it called a cis isomer, Self? Well, because the 2 CH3 substituents are on the same side of the molecule. What do I mean by that? Well, if I cut my line right down the middle here between the double bonds, right, I get a CH3 here, and I get an H3C here. Again, ambulance, right, in your rearview mirror, if you look at it, right, it's like still ambulance, but it's written backwards. Same thing here, okay? And on the bottom, you get an H, right? You get an H. Same thing if you look in your rearview mirror, right? If you put an H on the front of your hood of your car and you look at it in your rearview mirror, it's still going to be an H, right? So this would be called cis because they're on the same sides, right? They're on the same side. So hopefully right now you just had something go click in your head and you're like, oh, I get it. I get it, right? Because back here, a couple slides back, right? If we look back here, you don't have the same, right? You don't have CH3 and H. They're not the same thing, right? So if I was to look at CH3 head on or in my rearview mirror, it's never going to be just an H, right? They're not on the same side, okay? So it can't be. So it's not a cis-trans. But in this particular case, it is a cis-trans because CH3 on one side, flip it around to your rearview mirror, it's H3C, or vice versa, right? That's what makes it cis-trans. Isomer 4, what we get is trans-but2-ene, right? Because it's trans isomer, because you have 2 CH3 substituents are on opposite sides now. They're on opposite, one up high, one down low. Those are opposite, right? Almost diagonal from each other. But still, they're opposite because if you draw that line down the middle of the double bond, right, you got a CH3 up here, and then down at the bottom, you got an HC3. So they're on opposite sides. Opposite sides. So that would be called trans, right? Trans isomer. Not cis. It would be cis if they were both up top or both on the bottom. But because one's on top, one's on bottom, right, what you get is called trans isomerism, okay? And so it's not really that complex. You're just really looking for location of these things, right? If they are the same up top, one might be right-handed, one might be left-handed, spelled backwards or whatever. They're still the same number of atoms, right? Then you're going to get cis. But if they are flip-flopped and one's up top, one's down below, then you're going to get trans. That's all you're really looking for, right? Just the ability to recognize that mentally and then to know if it's cis or trans and name it. That's it, right? That's all I'm going to ask you to do with it. Cis and trans isomers, are they the same compound? Cis and trans isomers are considered to be different compounds, right? The cis isomer is more polar. Obviously, you've got both charges on top, right, versus the bottom, and it's going to create what we call polarity, right? Slight positive charge, slight negative charge. Think like a battery, right? The trans isomer has a higher melting point and is more stable than the polar one, than cis, right? So those are some nice characteristics you need to know, okay? Cis is more polar, while the trans has a higher boiling point. The trans has a higher melting point and is more stable. So if I were to ask you characteristics of cis and trans isomers, right here's the slide you need to go to. Again, write these notes down, put them down so that they're there for your resources, because I guarantee you're not going to go back and pull these up and listen to me go through this whole speech, right? This whole lecture to get back to this. So it is in your benefit to have you some bullet points as you go through here, right? And I know also you're not going to be able to always take the time to zoom through this as quickly as I lecture on it. So you're going to hit the pause button, right? And you're going to put down some points. That is the responsible thing to do as a college student. You're going to have to do this in order to succeed, through most of your college. So just get used to it. It's not a big deal, right? All right. Let's move on. Next slide. Maybe. There we go. Whoop, back up one. So this is where we're going to end. So if you have any questions over your cis trans, let me know. Right, I'll be shooting out some worksheets for you to look at with cis trans. Again, we'll meet tomorrow night at 6:15. You can ask me questions then about cis trans. But again, really the big key learning points to this whole lecture tonight, or this afternoon, would be: what is an isomer? What is a geometrical isomer? Right? What does it mean to be cis? What does it mean to be trans? How do we identify that? How do we name that? Those are the takeaways. That's all you need to be able to do. Okay, I'm not asking you anything else deeper than that. Do know those backslide, let's see, was it 20, I think, where you did the characteristics or the properties, right? You want to go back and remember that. But other than that, that's it. Right there, that one, that slide. Okay. But that's where we're going to end. Class is tomorrow night at 6:15. I'll post it on Remind. Anybody that's not available, that is, behind. I think I've spoken now with everybody, I think with the exception of Brooklyn. So I've not been able to get a hold of her. So if anybody can get a hold of Brooklyn, let her know what's going on, let her get caught up. That would be great. But that's it, right? And you're 4 to 5 weeks, you're going to be done with this. Okay. I want to make sure that everybody can get a grade. I don't want to give anybody an incomplete because you're missing work, okay? Because incompletes, typically once you're done with this class, you're not going to be sending me work through the summer, right? I've done this for over a decade. Nobody has ever turned in work during the summer, right? So take time, knock these things out as we go, ask questions as we go. You will pass, you will do fine, but you got to keep on turning stuff in. Right? Turning stuff in, asking questions, right? Keep up with it, okay? You're in college. Some of you are fixing to be seniors. Some of you are fixing to go to college for real, right? So keep up with your work, turn your stuff in, and ask questions, all right? So I hope everybody is safe and healthy. Stay in touch with me if you have questions. I will post this today and also post a little worksheet over some cis and trans isomerism. Okay? All right. Have a great day. God bless, and I'll see you tomorrow night at 6:15.